Okay, hey, welcome back. This is 3.4 Exponential and Logarithmic Equations. So we've done radical equations, we've done rational equations, we've done quadratic equations, we've done polynomial equations, we've done, was that all of them? Linear equations, I guess those are kind of polynomial equations. Just a whole lot of equations. Now we have exponential and logarithmic equations. Each type has two ways of doing it. For the exponential equations, you need not check your answer, but for the log equations, sadly, you do have to check your answers, Okay, so let's start with the exponential equations. And you've kind of already been doing this every time you evaluate a logarithm, exponential equations. Okay. So recall evaluating something like log base 3 of 9. What does that equal? So you think 3 to the x equals 9. 3 to what power equals 9? Well, 9 is really 3 squared, so x must be equal to 2. Guess what you did there? You just solved an exponential equation. And the property you used to solve that equation is called the, I think it's the one-to-one property. Okay. Crud. I didn't write that down anywhere. But anyways, the property that we're using here is basically if b to the m equals b to the n, then m must equal n. Okay. Yeah, it's the one-to-one property. Okay, so let me just write that one-to-one property. It's like when they introduce it in the book, it's not made explicit, but it is in the reading right above the yellow box when they first introduce it. So it's the one-to-one property you've been using to solve these equations. So let's now apply it, now that we know what we're doing, to some problems. So we have 3 to the x equals 81. Okay. So the deal is you want to get both sides to have the same base. So you can rewrite 81 as 3 to some power. So 3 times 3 is 9, times 3 is 27, times 3 is 81. So it must be 4. Right? And as soon as you have that, then you could just equate the exponents. So x equals 4, and that's your answer. Okay. Let's look at a bunch of variations of this. So 5 to the x equals 625. So 5 to the x equals 5 to some power, right? So 5 times 5 is 25, times 5 is 125, times that's 4 again. X equals 4. Okay. And then we start getting a little more complicated. 3 to the 2x plus 1 equals 27. Okay, so we want the same base. 3 cubed is 27. And then we can equate the exponents. Okay, so you get 2x equals 2, and then x equals 1. Let's get another. Okay, 625 is a power of 5. Just from that previous example, we kind of saw that. So what about 125? That also is a power of 5. That's just 5 cubed. Okay. We need to get both in the same base. You couldn't leave it as 125 like you're doing these others, because you couldn't get a 125 to some power on the other side. So our only hope was to rewrite the 125 as a power of 5, and we did that. Then we have this rule from exponents. If you have a to the x to the y, that's really the same as a to the x times y. If the other rule is a to the x times a to the y equals a to the x plus y, right? So our next step, we can rewrite 5 to the 3x. You just multiply 3 times x equals 5 to the 4th. And then we can equate the exponents. 3x equals 4. And then, of course, x is 4/3. Okay. More complicated now. So 7 to the x minus 2 over 6 equals the square root of 7. Rewrite that square root as a fraction exponent. Right? And then you can equate the exponents. Then you can cross multiply. So 2 times x minus 2, you distribute the 2, you get 2x minus 4. Add the 4 to the other side. Divide by 2. Okay. Let's look at another. So the natural base e. All right, so I need to rewrite the right-hand side in terms of base e. So using our rules of exponents, I could rewrite 1 over e to the 2x as e to the negative 2x. That's pretty simple. And then just equate the exponents. I'm going to move the 2x to the left, I'll get 3x. Move the 4 to the right, get negative 4. And divide by 3. Okay, so that's the first way, the one-to-one property. The second way is basically just taking logs on both sides. It's a little like squaring both sides or something like that. Okay, so the second way, take logs on both sides. Okay, so as an example, 10 to the x equals 8.07. So here we have no way of rewriting 8.7 in base as a base 10 to some power. So you're kind of stuck. So what you're going to do is use the it's the cancellation equations really. If you go log base 10 of 10 to the x, that's just going to equal x. Okay, and then on the other side you have log base 10 of 8.07. Okay, so on the left-hand side, again, I said that those are basically the cancellation equations. You just get x, and then on this other side, you get log base 10 of 8.07. And then if you put that in your calculator, you'll get approximately 0.91. Okay. Let's look at another. E to the x equals 0.83. Okay. So this time, to get the exponential to go away, you have to take log base e. And of course, log base e is our natural log. Truth be told, I always use natural log. I mean, that's easier on my brain. I don't have to, worry about, oh, which log do I use, which base do I use. You can always use log ln, log base e. Even in the previous problem, you could have used log base e. So anyways, cancellation equations, ln e, those kind of cancel, you get x. And then on the other side, ln of 0.83. Another example. In this problem, you have to isolate the exponential term. Okay, so what does that mean? That means this I want to get this e to the 7x thing all by itself. Okay, it's kind of like solving for that as a variable. So what you do is just divide both sides by 4. You get e to the 7x equals 10273 over 4. I avoid decimals because as soon as you start doing approximations, you'll get error, like snowballing. So I avoid the decimals. Now I'm going to take the ln of both sides. The ln of e cancel. If you don't like that idea of the cancellation equations, you could always do a power rule on this. And then ln of e, what is that? ln of e is the same as log base e of e. So you're asking e to what power equals e? And clearly that's just 1. So this thing is just 1. In other words, it's going to go away, so to speak, and you'll just have the 7x, which is what you would have had if you would have just thought of these as canceling out. Like ln of e cancel out, you're just left with 7x. Okay. And then finally, divide both sides by 7, and you'll have your answer. You can put that into your calculator, get an approximation if you're asked to do so. Okay. Note that 7 isn't inside of the log. So some people will try to, like, I don't know, squeeze the 7 inside the log. No, that log is separate. It's like a number unto itself. Anyways, this is approximately 1.12 if you want to check your calculator. Okay, another variation on this theme. E to the 4x minus 5 minus 7 is 11243. Okay, again, we want to isolate this exponential thing. We want to get it all alone so we can take the log on both sides. So I'll add 7 to both sides. 250. And then I'm going to take the log on both sides. Okay, cancellation equations gives me 4x minus 5 here. And then I got to solve for x. So add 5 to the other side. And again, that 5 doesn't somehow magically get absorbed by the ln. Okay, you can't do that. Just can't. No can do. Okay. Divide both sides by 4. And put it in your calculator and get your approximation. So if you want to check, to 2 decimals, 3.58. Okay. 2 more. This example is the quadratic form example. E to the 2x minus 3e to the x plus 2 is 0. So it has that x squared minus 3x plus 2 form. Okay? And if you saw that x squared minus 3x plus 2 form and you wanted to solve it, what would you do? Well, you would factor it, right? And that's exactly how you're going to handle this one. So instead of x, we have e to the x. Right? So it's going to be e to the x times e to the x, and then you need minus minus, and then it's going to be 2 and 1, I believe. Okay? And then you could set the parts equal to 0, and you'll end up with 2 exponential equations. Okay, so let's do the left one first. Isolate the exponential term. Take the natural log on both sides. And you get x is ln 2. Solve the second equation. E to the x is 1. And I already know that. It's just 0, right? You plug in 0. E to the 0 is 1. Okay. The next one, I always put a version of this on my tests. Okay, so you need to be able to master this. So it's a really good practice problem for doing algebra. Okay, so what do? I'm going to take the natural log on both sides. Then I'm going to pull down their exponents. And I have to put it in parentheses like this. Okay. Then I'm going to distribute the ln 7. On the other side, distribute the ln 3. Then I'm going to get all the x's on one side. So I'll move the x ln 3. I'll get minus x ln 3. I'll move the ln 7. I get minus ln 7. Then I'm going to factor out an x from the left-hand side. Then I'm going to divide both sides by the 2 ln 7 minus ln 3. Okay. And then you could plop that into your calculator and get a nice approximation. So you will see that on the test. Okay, so that's the worst. That's really as bad as it gets there. So let's move on, right? So we did the exponential types. Now we want to do the logarithms. And again, there's going to be two ways of doing these, using the one-to-one property, and then the other way is using the definition of the logarithm. Okay. So log equations, and in particular, one bummer or one cruddy part about all this is that you must check your solutions. Okay, so that makes these problems a little longer. Okay. So just like the rational equations, the radical equations, you got to go back and check them. All right, so the first type of way to solve these is to use the one-to-one property, or sorry, use the definition of the logarithms. And that just comes down to if you have log base b of m equaling c, then rewrite it as b to the c equals m. Okay, so let's take a look at some of those. Here we go. So, example. We have log base 7 of x plus 2 equals negative 2. Okay. So rewrite it. 7 to the negative 2 power equals x plus 2. So x will equal 7 to the negative 2 is 1 over 7 squared. 7 squared is 49. And then minus that 2. Rewrite 2 as 2 over 1. I need a common denominator, so I'll multiply top and bottom by 49. It's 98 over 49. And that'll equal negative 97 over 49. Okay. Now I need the check. So when you check, you have to plop that answer into the original equation. Okay, you can't like plop it in one step later. It has to be the original. So log base 7, negative 97 over 49 plus 2 equals negative 2. Okay, so you work the two sides separately. I mean, it's kind of like there's a divider line which you shall not cross. Okay? On the right-hand side, it's pretty much done, right? There's nothing to do over there. On the left-hand side, though, I have to do a bit of simplification. 2, we just figured out, is the same as 98 over 49. Okay, so 98 minus 97 over 49 is 1 over 49. And then you're asking yourself 7 to what power equals 1 over 49? And 1 over 49 is 1 over 7 squared, which is 7 to the negative 2. So 7 to the negative 2 is 1 over 49, so that must be negative 2. And it's a true statement, so therefore that is the answer. Okay, so x equals negative 97/49 is the answer. Okay. Okay. Let's look at another. Ln of the square root of x plus 4 equals 1. Okay, so this, the base is e, right? So it's really the same as log base e of the square root of x plus 4 equals 1. So we'll have e to the first power equals the square root of x plus 4. We'll square both sides. So you get e squared equals x plus 4. And then x equals e squared minus 4. Okay, got to check. So I have the ln of the square root of e squared minus 4 plus 4. On the other side there's 1. I have ln of the square root of e squared. So that is 1. And ln of e, the square root of e squared is e. And then ln of e is 1. 1 equals 1, so it's a solution, and you can circle it. There it is. Okay, it works. Check. Okay. All right, so you may have been tempted in this problem to convert that square root into an exponent and then use a power rule, and you would have been okay with that. You could do that. So these next problems, that's the kind of deal you're going to have to do. You're going to have to use properties of logarithms to turn it into this form where you can use the definition of the logarithm. Okay. So for example, log base 4 of x plus 2 minus log base 4 of x minus 1 equals 1. So first I rewrite it as a single log base 4 of x plus 2 using the quotient rule. And now I can apply the definition. So it's 4 to the first power, which is 4, equals x plus 2 over x minus 1. Then I can multiply both sides by x minus 1. And so I have 4x minus 4 equals x plus 2. Move the x over, so 3x. Move the 4 over, 6. So x is apparently 2. Then I have to go and check. And I'm working with the original log. So log base 4 of 2 plus 2 minus log base 4 of 2 minus 1. And we need to make sure that's the same as 1. Okay, so this is log base 4 of 4 minus log base 4 of 1. I'll make sure that's the same as 1. Log base 4 of 4. 4 to what power is equal to 4? 1. 4 to what power is equal to 1? 0. And then does 1 minus 0 equal 0? Or sorry, does 1 minus 0 equal 1? And certainly. So that works. And we can come over here and circle the x equals 2. Okay, we've not had any issues with answers yet, but in this next example you will see an issue. So let's take a look. This is log base 6 of x plus 3 plus log base 6 of x plus 4. And that equals 1. Okay, so first use the product rule of logarithms. This will be log base 6 of x plus 3 times x plus 4 equals 1. And then use the definition. 6 to the first power, which is equal to 6, equals x plus 3 times x plus 4. Okay, then we could FOIL out the x plus 3 times x plus 4. That'll give me x squared plus 3x plus 4x is 7x plus 12. It's quadratic, so move the 6 over to set it equal to 0. Okay. And then we can go ahead and hopefully factor. So we're getting x plus 6 and x plus 1. So our potential solutions, negative 6 and negative 1. We just have to make sure they work in the original equation. So x equals negative 6. We check that first. Log base 6 of negative 6 plus 3 is negative 3. Plus log base 6 of negative 6 plus 4 is negative 2. Equals 1. Okay, as soon as you get a negative inside a log, if this number here is less than or equal to 0, you're done. That means it's not a solution. Because you can't take the log of anything that's less than or equal to 0. Okay, so we throw that answer out. That's not going to work. Let's go on to the other guy, 1. So here we have log base 6 of negative 1 plus 3 is 2. Plus log base 6 of negative 1 plus 4 is 3. Equals 1. Then because the 2 and the 3 are positive, you can use the product rule to rewrite this as log base 6 of 6. Okay. And if you look above at that one that didn't work, if you did the product rule, it would seem to work, right? It would be log base 6 of 6. The problem with that is you've not fulfilled the restrictions, the constraints. You're not good. you put a negative inside of a log in the first place. If you go back and look at the restrictions on logs for doing the product rule, you'll see that this inner value has to be a positive real number. It can't be negative, okay, to do that. But here you can, because 2 and 3 are both positive. So anyways, log base 6 of 6, 6 to what power equals 6? And that's just 1. Okay, so 1 equals 1, that one works. And so we have one solution, x equals -1. Okay. Okay. The other property then is the one-to-one property. And we saw this property with the exponential as well. We just need to get a log on both sides. Like before, we got exponentials on both sides. So before, with our exponential equations, if we had something like a to the, I don't know, m equals a to the n, then m equals n. Okay, so now, if you have log of m equals log of n, then you could say m equals m. Okay. So let's look at an example of that. I have log of x plus 7 minus log of 3 equals log of 7x plus 1. Okay, on the left-hand side, I'm going to use the quotient rule to simplify that into one log. And as soon as I got that, I can go ahead and equate the inner parts of the log. So I'll have x plus 7 over 3 equals 7x plus 1. I multiply both sides by 3 because I hate fractions. I get x plus 7 equals, here, distribute, 21x plus 3. Then I'll collect all my x's on one side, so I'll have 20x if I subtract the x over. On the other side, if I move the 3 over, I'll have 4. And then solve for x, so it's 4/20ths, which is 1/5. Okay. I still need to check the critter, so check. I have log of 1/5 plus 7 minus log of 3 equals log of 7 times 1/5 is 7/5 plus 1. I have log of 1/5 plus 35/5 minus log plus 3 equals log of 7/5 plus 5/5. That's log of 36/5 minus log of 3 equals log of 12/5. Okay. Use a quotient rule. This is log of 36/5 divided by 3, which is the same as multiplying by 1/3. And then this will be log of 36 divided by 3 is 12/5. Log of 12/5. And then the one-to-one property, clearly that's true. I mean, they're both, okay, so good. Works. X is 1/5, and we're ready to move on in life. One little note, small note here, is that if you have something like the 5 minus the ln of, I don't know, x, you can also think of this as 5 plus -1 times ln of x. And then you could do a power rule. So that's the same as 5 plus the ln of x to the -1. You could literally bring this into and just use it as a power rule. And then that would be 5 plus the ln of 1 over x. So you can kind of avoid subtraction if you just think about it as a power rule. Anyways, let's look at one sort of application. And the exponential and logarithms comes up in modeling, mathematical modeling, when you're working with spread of diseases, growth of populations, radioactive decay, all that good stuff. So in this example, they give you a formula, A equals 25.1 e to the 0.0187 to the t times t. Then A represents the population in millions of people. In millions. And T represents the number of years after 2010. I think it's the population of like the United States or something, I don't know. So anyways, first off, they want to know the population in 2010. So what's the population in 2010? Okay. So, you know, you're just going to have to figure out T. So in this case, T is equal to 0. Okay. So the population at that time will be 25.1 times e to the 0.0187 times 0. Okay. And that'll be 25.1 times e to the 0. Anything to the 0 power is 1, so it's just 25.1 million. Then you could use this kind of to figure out when will the population be something. So when will the population be 28 million? Okay. So what you need to do is set that original equation equal to 28 million and solve. Okay, so you replace A in the original equation with 28. And then on the other side, you'll have 25.1 e to the 0.0187 t. You need to solve for t. Okay, so I need to isolate my exponential term. I need to get this by itself, so you divide both sides by 25.1. Okay, I'm going to take the ln on both sides. On the left-hand side, the ln and e cancel each other from the cancellation equations. There's something unsettling to me to have a decimal inside of a fraction, so I'm going to multiply top and bottom of this by 10, and that'll get rid of that issue. So that's a 251. Just too weird for me. I'm sorry. I'm not a traditional kind of person when it comes to math. Okay, so divide both sides by 0.0187. You get t equals the ln of 280 all over 251. Again, you can't smush the 0.0187 inside of the logarithm. Another decimal and a fraction. Yuck. Anyways, put that into your calculator and you get approximately 5. Okay. In other words, 5 years after 2010, so we're talking in the year 2015, the population will reach whatever the populace, 28 million. Okay, so that will do it. A lot of good stuff in there. We now can solve exponential and logarithmic equations on top of everything else going on in our lives. So thank you for watching, and I'll see you next time.